Oh, can I start?
Yes.
Okay. So the starting point of my talk is Szemerédi's theorem on arithmetic progressions. Proven in 1975. So Szemerédi's theorem says that any subset of integers with positive upper density this means that your set has positive density and has arbitrarily long intervals. So any subset of integers with positive upper density contains arbitrarily long, not trivial arithmetic predictions.
Completely out of focus.
What can people not see?
Focus is not.
Hmm?
So these are configurations of the form x plus y, all the way up to x plus.
Sarah, I think actually they will not be able to see below progressions. Yes.
Oh, okay.
And could you
Oh, I can just.
see yeah, there is definitely going to be that.
Does it help if I lift it?
Yeah, now it's feasible.
Okay. Okay, so not trivial. This means that y is 0. So this isn't just like the same integer k times. So by the standard compactness argument, this statement of Szemerédi's theorem is equivalent to the following. So that the largest subset of integers 1 up to n which, as in the last talk, we denoted brackets with n in the middle, with no k-term arithmetic progression. Of these things, has size little o of n. It's one of the central questions in additive combinatorics and combinatorial number theory. What is the largest size of such a set? So what's largest subset of integers from 1 up to n without k-term arithmetic progressions. Right, so that means getting like some sort of explicit bound, explicit upper and lower bounds for this little o of n term. Will people see if I can move this up? Yeah.
Yeah. Well, there's a reflex of the level, but I didn't see okay.
Okay, so I'll tell you a little bit what's known about this. So Szemerédi's original proof does, or I guess you can extract quantitative bounds, but the bounds are very weak. It's some weak bounds. Like the savings over the trivial bound of just n is like worse than like inverse tower type functions. Roth, actually earlier than Szemerédi's proof in 1953, for 3-term arithmetic progressions, So the Cocycles case got bounds big O of n over log log n. And this was done using Fourier analysis. And reasonable bounds, by reasonable I mean something that's not like savings, like an inverse power function, like something like a power of some finite number of logs. We're now going to work with Gowers in 1998 for four-term progressions, and in 2001 for longer progressions. So that bounds that are like a savings of a power of log log n. So I think it was n over log log n to the 2 to the negative, like 2 to the k plus 9 or something. And so in the course of Gowers' proof, he initiated the study of higher order Fourier analysis. Which I won't have time to tell you what that is. But so far, I've mentioned two proofs of Szemerédi's theorem, Szemerédi's original proof, and Gowers' quantitative proof. Another one I want to tell you about is Furstenberg's ergodic theory proof. In 1977, Furstenberg gave a proof of Szemerédi's theorem. Using ergodic theory. We introduced his famous correspondence principle. And so this proof doesn't give you quantitative bounds. And I guess there are people who like made some of the arguments like quantitative. But these still won't give you better than these like weak like tower type savings or inverse tower type. But Furstenberg's proof is very important because this method turned out to be like very, very flexible and led to generalizations of Szemerédi's theorem that we don't have proofs of in like for using other techniques. So method very flexible. And so one of these generalizations is the polynomial Szemerédi theorem. Which is due to Veblen and Lyman. In 1996. Which basically says that the kind of statement of Szemerédi's theorem still holds, even when you replace the polynomials y, 2y up to q minus 1 times y with like arbitrary polynomials. As long as you avoid some kind of arithmetic obstructions. So if we let 1, yeah, integer polynomials, they all having 0 constant term to avoid like congruence obstructions to the theorem being true. Then if A is any subset of integers common to F, no non-trivial configurations of the form x plus p1 of y, all the way up to x plus p of y. Then set of A is little o. Another generalization is the multidimensional generalization. Which was proved in, I think, 1978 by Furstenberg and Katz-Nelson. It says that we let S can be non-empty and if A is a subset of integers 1 to n to the d, and it has no non-trivial homothetic copies of this finite set. So no, as in for A plus B times S with B not equal to 0. And below entity. So it's a difficult but interesting problem. Difficult, interesting generalization of the problem here of finding bounds in Szemerédi's original theorem. Find bounds in these generalizations of Szemerédi's theorem. So bounds in these generalizations. So a lot of what I did in grad school was related to proving bounds in the polynomial Szemerédi theorem. So for a long time, there were only bounds for two-term progressions that could be attacked using the circle method, and for kind of progressions involving linear polynomials, which are just some sub-progression of some sufficiently long arithmetic progression. And related things like arithmetic progressions with common difference equal to like a perfect cube. But all these configurations they're related to arithmetic progressions are really special because they're translation, dilation, and variant. So kind of Gowers' method doesn't really work for the vast majority of polynomial progressions. So what I did in grad school was prove out the polynomial Szemerédi theorem when all of the progressions, or when all the polynomials have distinct degrees. The bounds that are like a power of like low log, when pi has distinct degrees. But what I actually want to talk about in my remaining time is something that I can't do, which is what's in the title of the talk, saying anything about squares in dense subsets of the n-pi integer grid and 1% Cocycles. So the multidimensional Szemerédi theorem. You still know like barely anything. We only have quantitative bounds for things that are basically some arithmetic progression, like a point. So you can just look at like each, like kind of each of the like cosets of like this line and apply some theorem on each of them with quantitative bounds, or that's equaling is that 0, 0, 1, 0, 0, 1. So this corresponds to asking for what's the largest subset of a 2 by 2 integer grid with no corners. So looks like this, where these sides have the same length, and bounds for set left in this configuration approved by Schweda in 2004. And this is it for the multi-dimensional Szemerédi theorem. We don't know bounds for any other configurations. In particular, we don't know anything about what if you add the last vertex of this square. So what's the largest subset multi-dimensional grid with no 4 vertices of an axis line square? So something that looks like this. This is related to the following question that looks like it's totally not even relevant. The question is, I guess the problem is to classify functions from, say, there's not n, plus there's not n, satisfying the 2 cocycle equation in group homology. I get the signs right. For 1% of the 3 tuples x, y, and z. Say for 1% of x, y, and z. So kind of understanding this problem is necessary for efficient draw to an arrow. So understanding this is necessary for kind of any sort of higher order Fourier analysis approach to this problem, but it's not sufficient. But I still have no idea how to do this. Okay.
Questions?
So the conjecture would be that this must agree with the genuine cycle on some kind of arithmetic progression, large arithmetic set.
So I think you have to be a little more careful because you can embed like a 2 cocycle on like z mod like pz cross z mod pz like squared for like p like the square root of n. You can like embed that like as a function on these groups.
Yeah.
So I think we don't even know like what the conjecture should be. Like maybe you should allow for these things, but maybe have a bound on the rank depending on what 1% is. But maybe there are like examples that we like haven't thought of yet.
I'm a bit confused. You presented a lot of stuff. The Furstenberg theory and Katz-Nelson and Hales-Jewett is all little o. You want to quantify it. Did you quantify all of Hales-Jewett yourself or something?
No.
So this last question is understood with little o?
Yeah. So this is understood with little o through like the Furstenberg Katz-Nelson thing, and also there's a couple of hypergraph regularity proofs of the multidimensional Szemerédi's theorem. Okay,
so it's an issue of quantifying with something which is better than little o. That's the question in this last question.
Yeah, so I think the same way that you can extract like some really weak bounds from Szemerédi's original proof, you could also get like a savings that's like inverse Ackermann or something from these hypergraph regularity proofs. So the question is, I guess, get something that's like a savings of like some finite number of logs.
Yeah. So I have a question then. In your quantification, do you ever face null manifolds or some translation of null manifolds into a different language?
So in the polynomial stuff, it turns out, even though higher degree Gowers norms, like arbitrarily high degree, things show up so that if you were to like kind of argue in the normal way, you would have to, you know, use the inverse theorems for these norms and then deal with like Hill manifolds. But I actually found a way around that where you never have to use these inverse theorems. All you really need is the inverse theorem for the U2 norm, which is just Fourier analysis.
Okay.
So even though some like arguments say like, oh, you should study like the U10 norm, actually showed you can use kind of the polynomialness of this to say, no, now you should study the U9 norm all the way down to the U2 norm.
Okay. Thanks. Yeah, that helps. Thanks.
There does not seem to be any other questions, so thank you.